In this video, you'll see what happened when I took one of the fastest ready-to-fly RC planes in the world, whoa, and attempted to make it faster using some extreme upgrades, eventually testing multiple rocket engine boosters grouped together in a mission to find out whether the plane would go faster or explode into 1,000 pieces. I've built loads of high-speed aeroplanes before, but none quite like the plane in this video. It's an already very fast RC plane that is advertised as being able to fly at an eye-watering 130 miles an hour in a dive. So this would be one of the fastest planes I'd ever tried upgrading on the channel. So in this project I wanted to 1. See how fast the plane would go with electronic modifications, and then 2. Increase that speed even further with rocket engines grouped together in a way that I've never tested before. How fast would it go? And would it survive? I was excited to see what this thing could really do in the real world. So after around 10 minutes of assembly and setup, it was time to head out to the test field for the very first test flight, to see how fast the plane would go as a completely unmodified aeroplane. Right, so I'm using a GPS to measure the speed, so let's see how fast this plane can go. It's nice and smooth. Right, just getting used to it. It needs a bit of trim. Right, I've got it trimmed out. Let's see how fast we can push it. Throttle up. Whoa, that's so smooth. Throttle back, come out the top of the curve, roll level. Safe select autopilot on. It's not really an autopilot, but it helps a little. Okay, let's do another one. Coming down nice and straight and level. Whoa! I don't know what speed that would be. I'm not used to a high-speed plane being so smooth. All my homemade ones are all a bit all over the place. Right, let's land it and see what speed it was. With a rocket engine, this is going to be ridiculous. Oh, that looked amazing. Right, let's see how fast this thing went. Stop recording, read. 152 kilometers an hour. So that was 94 miles an hour. A good start, but I thought we could get this thing to go a bit faster. Right, now we have a benchmark speed, we're going to do a few modifications to the aircraft to make it go faster. And the first thing that we're going to try is to streamline the onboard cameras. For this project, we would need at least one onboard camera to monitor what was happening on board the aircraft, as it was quite difficult to see things from the ground. The problem was gluing these cameras directly to the wing was creating a lot of drag, and we could see this really well using a virtual wind tunnel. So I decided to cut a hole in the wing of the plane to hold a single camera, and this would lower its frontal area. Next, I could design some simple aerodynamic fairing parts and print these out on a 3D printer. When fixed to the wing, now this single rearward view camera looked like it would have much less of an impact on the drag of this aeroplane. And we could see that this was actually the case on the CFD software too. Hopefully, we'd now be able to hit some higher speeds. So now we'd made the plane more efficient, we could next work on adding more power. The plane had a very powerful motor, but the stock 4-cell battery only provided it with around 14 volts. I knew we could probably squeeze a bit more out of this motor without burning it out, so I decided to risk using a 6-cell battery with a nominal voltage of around 22 volts to increase the RPM of the motor dramatically. The problem though was that I'd have to upgrade the other electronics to deal with the extra current. So I soldered some connections to a new speed controller which could take more amps, and then crammed this into the very space-limited nose of the plane. Now to test the motor to see if it would turn faster, firstly with the original battery as a benchmark. The plane was now ready for its next test flight, and I was excited to see how fast it would go now with its more optimized aerodynamics and higher voltage battery. Right, it's looking a bit rainy and a bit windy, but it's just about flyable conditions, so yeah, let's make some progress. So I'm going to do one slower pass. We'll try and get that to about 100 miles an hour, and then we'll go for a faster pass. So here's the slower pass coming in. Okay, 50% throttle. Okay, it doesn't feel that much faster. Nice! With the increased power, the plane was flying even better than before, but it was looking like we were getting a bit of flexing going on in the tail during turns. Hopefully this didn't get any worse. Okay, and then we're going to push, that was about 70%, now we're going to push it to 100. Coming down now for approach. 70, 80, 90, 100! Nice, the thing held together. Should we do one more? I'm gonna put the power back on, 10%. Okay, coming down now for another fast approach. Oh, that's crazy fast. Nice! Yes, it survived to fly another day. All right, let's see how much faster that was that time with the GPS. So the last speed was just under 100 miles an hour. So yeah, we're looking at about 160-ish to beat. 190. Okay, so that's, what's that? It's not that much faster actually. It's like, yeah, I thought it would be a lot faster than that. So the plane had gone a bit faster, but not as much as I'd thought. But this might have partially been due to poor conditions with an awful lot of water molecules hanging around in the air. Now it was time for phase 2, where we would take this plane to the next level with some rocket boosters. Okay, so the thing about this rocket plane is that it's going to be quite different to my other rocket planes I've designed on the channel before. And this is because it's going to use a cluster of rocket engines, as I want to see if this is a better way of boosting a speed plane. All of my previous rocket planes, like this one, have used one single large engine on the top of the fuselage. But this can be a bit of a problem, as when it fires, it can push the nose down. So this new rocket plane will have several smaller motors attached to the wing of the plane, aligned with the lateral center of gravity, meaning the plane won't pitch up or down during the ignition of the motors. The rocket motors I would be using were small black powder rockets, usually intended for the hobby of model rocketry, and I got a load of them online for this project from a model rocketry shop. I decided to run a few tests, as I wanted to make sure that this batch that I'd got didn't have any duds. An asymmetrical ignition would be game over for this project, so this was important. 3, 2, 1. 3, 2, 1. Yeah, it was a bit smokier than I was expecting, that one. The way these model rocket motors work is really quite simple. When ignited, their solid fuel, which contains an oxidizer, undergoes rapid combustion, which forces hot gases through a clay nozzle at supersonic speeds. This generates a strong pushing force in the opposite direction. To harness this strong pushing force though, we would need to build some strong rocket engine mounts on the aircraft. So I headed back into my CAD software and got to work adding some to the model of the plane. By the way, the software that I've been using throughout this project to design all of the 3D models is called Onshape, and Onshape are actually sponsoring this video with an ad. Now what's great about Onshape over other CAD packages out there is that everything is done in the cloud, which means that it can never crash and you can never lose any data. This means that there's no installations, there's no downloads, and everything can be done on a computer that's not even that powerful. This also automatically enables secure real-time collaboration, which is helpful for simultaneous editing with teammates. I can really easily share anything with teammates like Emma, who's on the other side of the room, without having to send things via USB stick like I used to do. That's the analog way of doing it. Emma actually designed the Electrostreak model. How was it?
Pretty intuitive. I actually quite liked it.
With the projects themselves, Onshape tracks all activity and has infinite restore. So this can be a big worry off your shoulders if you're working on a fast-evolving, high-stakes project like the one in this video. Onshape includes built-in PDM with branching and merging, along with multi-part part studios. And if you're wondering whether this stuff can do proper engineering, not just DIY stuff, companies like Garmin and even Boom Supersonic, which I'm obviously a big fan of, have moved to using Onshape for all of their design work. So if you're an engineer, definitely check out Onshape with my link in the description to get up to 6 months off the Pro version for free. Thank you very much to Onshape for sponsoring this video. Okay, so now we had a design for the rocket engine mounts, it was time to get stuck into making them in the real world. For this, I used model rocket components, cut to size and fitted with some 3D printed aerodynamic noses. After a bit of paint to make them moisture resistant, they were pretty much ready for mounting. But first I wanted to make the aeroplane a bit more visible in the sky to make it stand out at higher speeds. Just like the Bell X-1, the world's first supersonic aircraft, I painted the plane international orange for maximum visibility from the ground. Now we had the plane all painted up, I could next make the strong plywood brackets that would hang the rocket engine mounts at the correct position along the lateral centre of gravity of the aircraft, so that they wouldn't pitch the plane up or down when they ignited. To make these mounts as strong as possible, I cut the parts from some aerospace grade plywood on my Bamboo Labs HTD laser cutter and embedded them deep into the wing with plenty of glue. Now it was time to add electronics to remotely activate the rocket engines mid-air. For this, I would use some RC switches that would send power from an extra battery to the rocket engine igniters. Of course, I had to check if this would work, though. 3, 2, 1. So one igniter worked, but what about 4? Each of these igniters would need to go off instantaneously if we were to get reliable simultaneous ignition of each rocket motor. If one failed, it would be a big problem. Okay, test of 4 at once. 3, 2, 1. Ooh. So, after wiring the new electronics into the wing of the plane, our new speed plane was now finally ready for its big test. The engines were prepared, the electronics extensively tested, and the weather was looking good. But would the plane successfully fire its multiple engines together, or would it rip itself apart mid-flight? Okay, that's down. As always with these projects, there's always a lot on the line when it comes to these test flights. As if just one thing breaks, it can be game over. So there are a lot of things that could go wrong with this, as always. The first thing I'm a bit worried about is that these rocket pods won't actually hold up to the forces involved with boosting this aeroplane through the air. The other thing is that I'm a bit worried about tail flutter. And finally, we could have an asymmetrical ignition of the rocket engines, so we could have one fire on this side and one not fire on the other side. So we're going to just kind of accept that this is a very risky project and that this aeroplane is probably not going to come back today in the same shape that it is right now. Consulting my checklist, I installed the first rocket engines, 2 C-sized engines that would produce a D-size impulse of around 3 kilograms of thrust over their 2-second burn time. The igniters were next, and these had to be very precisely fitted so that the igniters were in contact with the fuel. Okay, it's very important that we get this right, otherwise it's just going to spin out of control, even on this lowest power. The first flight, we had decided, would not try to achieve a higher speed. Instead, I would ignite the motors at around 50% throttle. This way, if anything went wrong with the ignition, the plane would probably still survive at these lower speeds. We would use it as a trial run for the larger rockets. Okay, ready? Mm-hmm. Okay, here goes nothing. Starting my turn, coming down range.
Successful ignition!
Success! Both rockets had fired and the plane was still in one piece.
Okay, and we have ejection of the motor casings. Now I just need to land the thing. Keep it in one piece for our next test. Okay, off the power. I hope that they've stayed intact.
A bit crunchy.
Oh, we've broken a prop. That was the noise. Well, I prefer to break a prop than break the rocket pods. And the rocket pods are intact.
It seemed like we'd achieved the first project objective to prove that multi-engine rocket plane flight was possible in RC form. Now we could size up and see if we could increase our previous speed record with 4 C-size motors, which would double our impulse, with around 6 kilograms of thrust over 2 seconds, equivalent to a single E-size rocket motor. 6 kilograms was going to be quite a lot of force on this airframe. So would the aircraft survive this next flight?
Okay, go for launch. All right, let's turn around. Okay, increasing throttle. Oh, we've had a disaster. The rocket engine's ripped off. So we're going to come in for an emergency landing.
Now I had a big job on my hands to get this plane down. The ailerons were hanging on by a thread, but could I get it home?
It's flying all over the place because of the asymmetry. Watch out! Oh, oh, crash landing!
The plane was down, minus half of its rocket pods.
Yeah, these just completely ripped off. Look, it ripped off not just on the foam. So actually the wood, because this piece actually went all the way through the engine to here, it looks like the plywood actually sheared. Look, even the carbon spars coming out of the wing. Wow, I thought I saw it flexing. Maybe I think it must have oscillated and then ripped off the engines as it was vibrating.
Nice flex.
Sadly, the plane was not repairable in the field and hadn't even gone any faster on that last test flight than the previous fastest electric-only flight. But could we rebuild and go again? First, we needed to assess the footage of the onboard camera to see what had happened.
You can see the aileron actually fluttering there already. Oh, there we go. Oh, whoa, that was so violent. Yeah. That's amazing that the wings actually stayed on. Oh, the whole aileron almost ripped off.
The simultaneous ignition of the rocket motors had been successful, but the 2 rocket pods had detached due to catastrophic aerodynamic flutter.
Oh, it was okay for the first few seconds, and then it just... Oh, that was one of the most violent failures I've seen for a long time. I'm quite amazed I managed to bring that back in one piece, to be fair. That was one of the more sketchy landings. Look at the aileron almost coming off even there.
So the plane hadn't been rigid enough to deal with the force of the rocket engines firing under its wing. It had caused an extreme amount of flutter due to the wing being too flexible, meaning it twisted under load. And this had then ripped the engines off the wing, with them failing at the plywood supports. We had found the limit for this plane. We had successfully increased the speed of the stock aeroplane and found it was possible to ignite multiple rocket engines to boost a plane's speed. I think this all goes to show that with DIY engineering, even if not everything goes to plan, you can still make a lot of progress and have a great deal of fun along the way.
Assessment?
Yeah, maybe not this design next time.
Yeah.
Time to design the next one. Thanks very much for watching this video. If you enjoyed it, then check out another one over here. I think you'll like this one next if you got to this part of this video. And yeah, also make sure to give this video a like and subscribe to ProjectAir down below. Also make sure to check out ProjectAir 2, as that's a channel all about how to build your own RC planes and things like that. And yeah, I will see you on the next project. Bye for now.